Good morning, geometry students. One day closer to being done. Yay! Anyway, Monday I have designated as a work day for the assignment that goes with this particular lesson. So today you're watching the lesson, you're taking notes, you've already submitted assignment 58, hopefully, and then Monday, during the time you would have spent watching a video and taking notes, you'll be working on the assignment, and then by the end of Monday, you'll be making sure that you turn in assignment 59. So that's just how that works. Now, I know that here's this word. It's not meant to be a scary word, proving similar triangles. The whole purpose to this section is so that you can look at triangles, determine whether they're similar, and then after you know that they're similar or not, then you can do the proportion thing and figure out some missing pieces. So we're going to look at it in that way, but you do need to be able to identify with a picture the reason why two triangles are similar. So we have a couple of postulates that we're going to talk about today. One of them is called the angle-angle similarity postulate. Now, we already had something very close to being that same postulate earlier when we knew that two angles are congruent means that the third angle is congruent. And so two angles being congruent is sufficient for showing that you have similar triangles. Once you have similar triangles, then that tells you the sides are proportional, and then that can be very, very helpful in certain things, in certain areas. So let's take a look at this picture and kind of analyze what's happening here. If two angles are congruent on one triangle to the two angles in a second triangle, the triangles are similar. Well, just to remind you, these markings right here mean these lines are parallel. So since these lines are parallel, that means that the alternate interior angles are congruent. So all of a sudden you have two pairs of congruent angles in these two triangles, which means that you've got similar triangles. Okay, you can also think, if you didn't want to do this one, this one, this one, this one, you could also think about the vertical angles which are congruent, which once again, as long as you have any two angles of the triangle that are congruent, it means that the triangles are similar. Now you do have to be careful when you're labeling them. As far as putting the corresponding parts together, A and E are ones that are the same. B and D are ones that are the same. And then C is congruent to the other C. I can't say it is congruent to itself, yes, but this angle C is in a different triangle than this angle C. They happen to be congruent, but this one is ACB and this one is DCE, if you remember. So we know the triangles are similar. Why we care, I said a second ago, is because once we know that they are similar, we also know that the sides are proportional, which can be helpful, and we'll be doing a couple of problems regarding that. So one of the things you look for to prove or to show or to be able to determine that triangles are similar is the angle-angle similarity postulate. And in a test or quiz setting, you would be asked to give the reason how you know that they are similar, and it would just be simply, you could just write angle-angle similarity, or since we're typing things out, A, and then the word similarity. That's not too hard, and it's a lot easier than trying to find this symbol somewhere in your keyboard. Okay, so another one is the side similarity postulate. Okay, side. We had our congruence postulates, so these should look somewhat familiar to you, but instead of congruent, side similarity says that the sides are proportional. Okay, the sides are proportional. The sides are not actually congruent, because if the sides were congruent, they'd be congruent triangles. Okay, so if all three sides of one are proportional to the three sides of the second one, in other words, the ratios are equal, then the triangles are similar. These three triangles do happen to be similar because let's check out our proportions. 4/8 is a half. 5/10 is a half. 3/6 is a half. That makes this triangle and this triangle similar. Okay, let's check out the relationship between this one and this one. 8/2 is 4. If you take 6 divided by 1.5, you get 4 again. And if you take 10 divided by 2.5, you'll get 4 again. So this big triangle and this little triangle are also similar because the ratio of the sides is giving you the same number in all the cases. Once again, let's check out this triangle and this triangle. Now, you should know and understand, even though it's not a postulate or theorem, but because they're both similar to the same triangle, they have to be similar to each other. It's kind of like it's really a commutative property of similarity, but they don't put that in as a theorem, but it should make sense to you. So I'm just throwing that in there. All right, let's compare this one to this one just to kind of make that make sense to you. 4/2 is the same as 2. 5/2.5 is 2. And 3/1.5 is 2. The ratios are the same for each one of the sides for these two triangles. These two triangles are also similar. So we have all those things going on and able to be able to show that you have got similar triangles. Okay, so we have two so far. We've got angle-angle similarity. We have side-side-side similarity. It's a little harder to apply side-side-side similarity, but if you only have side lengths, then that's what you have to go for. And once again, the reason that you're showing that is because once you know that your triangles are similar, not only do you know things about the proportional sides, which this already was pre-done for you, but you know that the angles are congruent. It also, it just helps you figure out a whole bunch of other things too, because if things are similar in size, then that means that especially if you're doing something on a computer and the aspect ratio is the same, in other words, the picture looks the same enlarged as it does smaller, that's useful to you because if you enlarge one dimension and not the other, you end up with a really weird looking picture. It can be fun in certain things, but similarity is when you want something to look the same, just a different size. Okay, so now this one, called the side-angle-side similarity postulate. So far we've got, this is our third one, angle-angle, side-side-side, and side-angle-side similarity. And so on this one, you have two sides and two sides of one triangle and two sides of a second triangle are proportional. And then you've got the included angle is congruent. So sides you're always thinking about is in terms of proportionality, and the angles you're thinking about as being congruent. So let's think about what that looks like in this picture. Okay, sides proportional, the angle that's included between them has to be congruent. Okay, so let's take a look at that. I want to bring it out just a little bit at a time here. Okay, let's get these things here. Okay, now in this case what we're focusing on is this triangle here and the larger triangle that kind of encases the smaller triangle. They're sort of overlapping, so we need to consider them. So I'm going to compare, if I'm thinking about the small triangle compared to the big triangle. If you compare AB to AC, we can find its ratio. Okay, so 4 compared to 6. Be careful you're comparing the 4 to the 6, because 4 is a side of the triangle and 6 is a side of the triangle. 2 is just helping you to find out that together they make 6. So my comparison of this side of the triangle on the small one to this one on the big one is 4 to 6, which reduces to 2/3. Little triangle comparing to big triangle. AE is the little triangle equivalent to AD of the big triangle. So I need to compare their proportions. I'm comparing 5 to 7.5. Okay, and that also equals 2/3. All right, you have a couple of options here. You can either use a calculator that will reduce that for you. Okay, you can either use a calculator that will reduce that for you. That's the last class's lesson. 5 divided by 7.5. Using your Math Frac button. Now here's the thing, if you don't have this calculator yet, it's a good idea to buy one. You're going to use it a whole lot in Algebra 2. I know we used it a little bit in geometry, but you're going to use it a whole lot in Algebra 2. So you need to have one. So you may as well just go ahead and get one so you can hold it in your hand, so you don't have to try to go back and forth finding simulators and those type of things. These things can be carried with you to your SATs. So it's just a good idea to buy it now, rather than having to scramble at the last minute for it. So put it on your list, something that you need to get. If not by the end of the school year, get it over the summer so that you have it for next year. Super important. Okay, so here's your 2/3. Okay, so this one and this one have the same ratio, which means that they are proportional. We did that yesterday. Okay. So since those two are proportional, now what we need to do is find that angle. Okay, so here's the thing. When we're looking and comparing this triangle to this triangle, they both share this point right here. They both share this angle. Angle BAE is the same as angle CAD. And so since they're the same angle, they are congruent because reflexive property tells us that. I'm not really doing this as a formal proof. However, if you had something like this, you would need to check to see if they were proportional. See if you can find that included angle, and then you would be able to give as a reason that these two are similar because of side angle side similarity. Triangle ABE is similar to triangle ACD, and our reason would be because of side angle side similarity. Your job would be to find these pieces, be able to recognize a figure and why they are similar. And I have some examples here we're going to go over a little bit at a time to make sure. So I'm going to show you the examples. You can take a couple minutes to write them down and anticipate what you think will be the answer. And once you do that, we can go ahead and go over them, and I'll show you why. Some of you may have already figured out by then what they are, but here's our pictures we're going to analyze. And we're going to determine which of these we have enough to show that they are similar. Okay, and if we have enough to show they're similar, we're going to say why. We have three choices. We have angle-angle similarity, side-angle-side similarity, and side-side-side similarity, and that's it. Okay, beyond that, we don't have anything else to go on. We don't have a whole giant laundry list like we did for the congruent triangles. All right, so we're going to take a look at this one. You're going to probably pause it and take your time on this, especially since Monday is just a work day, not just because it's a lot of work to have a work day, but today you're focusing on understanding this. Okay? All right, this one. They are similar. It is important to be able to line them up, but look at the picture. The two sides are congruent. Not two sides, the two angles. The two angles are congruent. So since the two angles are congruent, you don't have to go any further. You don't have to look for anything else. Angle, angle means that they're similar. The hardest part for you is going to be to make sure that your similar triangles are in the correct order. Triangle Q, T, U. Okay, R goes with Q, those are the unmarked ones. T goes with T because they're marked congruent, and S goes with U because those are also marked congruent. So they are similar triangles. Triangle QTU is similar to triangle RTS because of angle-angle similarity. Okay, so we have that. Then we had this picture. On this picture, we're given nothing except for sides. So what you need to do is we need to double check and we need to make sure that the sides are proportional. So we're going to need to be lining up the parts that would be possibly congruent or possibly the ones that line up. The triangles kind of look the same but also kind of different. So when we do try to check their proportions, okay, you can go by longest to shortest. That's the best way to make sure that you're picking the right ones. So for example, this is the longest side of this triangle. This is the longest side of this triangle. You need to check the proportions between them. So 4.5 over 3, which when you reduce it would be 3/2. The smallest side is 3 and 2. And you go by the numbers, smallest and smallest. Smallest of this triangle over smallest of this triangle. And we get 3/2. That leaves just one other number. This one is the middle number in each one. 4 over 2.5. But when we change that one into a fraction, okay, when we change that one into a fraction, I take 8 divided by 5. Or I take 4 divided by 2.5. And then you turn that into a fraction. What we find is that 8/5 is not the same as these two. Even if you didn't have it as a fraction, okay, say you had to use a calculator from your phone or whatever, okay, whatever calculator you're using. You could do it all in decimals and do 3 divided by 2. And that gives you 1.5. 8 divided by 5, which gives you 1.6. And then 4.5 divided by 3, which gives you 1.5. So your 1.5 would match your 1.5, but your 1.6 wouldn't match. Because in order for it to be similar triangles, all three of these have to be the same ratio, not just two of them. Okay, I'll say that again. In order for them to be similar triangles, all three have to be the same ratio, not just two of them. And once again, the lining up in order, smallest, largest, middle, tells you which one goes with which one. Okay, let's look at another one. Okay, we had this one. This one's a little interesting to think about, okay? Yes, I have that there, so I may as well just leave that there, but let's think about it. We have triangles that we're trying to compare. I believe that in the original problem I told you which ones to compare. No, I didn't. Okay. Well, anyway, we're trying to compare triangles. So GHJ and JHI are the two most obvious triangles to compare and see if they are similar or not. Okay, this little one over here and this little one over here. So we have some things that you can tell on these are congruent or similar, or find their numbers that go with them. One of them is that whenever you have a perpendicular line, it means the angle on both sides are 90, which makes them congruent. So these two, JHG and JHI, both right angles, making them congruent. So we've got our angle part. Remember, you're either looking for angle, or side angle side, or side side side. We don't have all three sides in either one of them, but we do have two sides and we have an angle, so the only one it could be would be side angle side. So you're going about your business to try to make sure that those pieces all make sense. So we have our angle. Once again, if you go by smaller and you go by larger, that will make sense. So this 4, when you're looking at this triangle and you're looking at this triangle, this 4 is the smallest side of this little triangle. This 6 is the smallest side of this triangle right here. So if you're comparing from this triangle to this triangle, 4 goes with 6. Okay, now that takes a little to get your head around if you can mentally pull this triangle separate from this triangle. 4 is the smallest side of this little one, and 6 is the smallest side of this big one. So 4 over 6 is the same, we reduce it to 2 over 3. Over here, this one is the longest side. It's the longest side of the little triangle. And HI, it's the longest side given. Okay, we've got the hypotenuse and the hypotenuse, but it's the longest side given. So it's the longer side, and this is the other longer side of the bigger triangle. Longer side of the smaller over longer side of the bigger, which also reduced to 2/3. Since these reduce to the same fraction, and they are the sides that are around the congruent angles, these two triangles are similar because of side angle side similarity. All right, it takes a while to get your head around that. You might want to backtrack over that and listen again. Okay. All right, let's look at that fourth one. The fourth one had 3 sides again involved. We don't have any angles involved, so we needed to check them. We have a small one, a medium, and a large. Smallest, next, largest. So you compare the smallest sides, and we get a fraction. We compare the largest sides, smallest to largest, smallest to largest. We get a fraction. We compare the middle sides, and we get a fraction. The fractions all come out to be the same number. Okay. The similarity ratio, let's bounce back to last section real quick. Similarity ratio is that number. Okay. We could also call it the scale factor. Either one of those words works just fine. Okay, the scale factor or similarity ratio. All right. Moving on another step. Okay. So far we've just been practicing, showing that they are similar. Okay. Once you know, at least mentally, how to check that they're similar, Then you can use that to find missing pieces in a situation like this. This would be used if somebody was doing something like surveying. Surveying is a job where you go around and you figure out the exact boundary lines of people's properties. Before you buy a house, the property has to be surveyed and they have to put in new stakes to make sure that nobody has built something over a line. Before somebody builds a building in a city, they have to survey it and make sure that nobody has built where they're not supposed to build because it's not their property. Okay, so surveying is definitely something that some of you could possibly look into for a career, but it's all based on being able to find out what goes where, a lot of angles, a lot of figuring out distances in that. Okay, so here we have these two triangles. They are similar. This is kind of like the example we talked about before. If you have these lines marked parallel, then we know that these two triangles are similar by angle-angle similarity, but we're not asking that question. We're asking to find x. We're trying to find the missing piece. So what you're needing to figure out is which two triangles are similar here. This one is similar to this one, so you have to figure out which piece goes with which piece. Okay? So the 9 and the 21 are kind of the obvious ones that go together. Okay? 9 over 21. But which side, the 8 or the 6, would be in the proportional position for the x? Okay, well, you have to look at what angles you know are congruent for that. Okay, so this angle is congruent to this angle. And this angle is congruent to this angle. And this one is congruent to this one. So what that tells me is because these, let me get another color, these are congruent. And these are congruent. Okay. So the one that goes from red to blue here is the 8, and the one that goes from red to blue here is the x. So the 8 and the x are the ones that go together in that particular scenario. The 9 and the 21 are a little more obvious, but in order to figure out which one, if you mark up your picture a little bit, colors or similarity or congruent markings with the right number of little swoops, then you will be able to see which ones go together. So the 8 goes with the x. So 9 goes with 21. 9 is part of this little triangle, 21 this triangle, like 8 goes with x. 9 goes with 21, like 8 goes with x. 9 goes with 21 like 8 goes with x. We use a cross multiplying trick and you divide it out. Calculator shows 56 thirds, but let's just remind you a little bit with your division right now. If you take 56 and you divide it by 3, we get 1. And we get 8. And you have 2 left over. Remainder over divisor, so 18 and 2/3. Okay, calculator is showing 56 thirds, but in order to make it useful, 18 and 2/3 inches is more useful. And especially if we were writing it down, I would be a big stickler for no decimals and rounding and those type of things. We'll see how that plays out as we go through the next couple of weeks here, but just be careful that you can make it into a mixed number or into a fraction or into a decimal. Okay, all those might be important. Okay, so here 18 and 2/3 inches. Okay. All right, one more, and this one's really interesting. It's a word problem, okay? And that's really what all of the geometry is useful for scenarios that you could encounter. So even though it said proving triangles are similar, it's a useful thing. It's not just a random thing. So let's take a look at this one. You need to buy enough paint to cover the front of a building. So get a mental picture of a building and you're trying to paint it. The building is 40 feet wide and it casts a shadow that's 8 feet long. At the same time, your 5'6" friend casts a shadow that's 3 feet long. How many cans of paint will you need to buy if each can covers 400 square feet? What? Okay, so here's the thing. You're not measuring right now the height of the building. Okay, later on you can use your paint rollers or your scaffolds or whatever, but you need to just find the quickest way of figuring out how tall that building is so you can figure out its area, so you can figure out how much paint to buy. So we need to consider what's happening with your friend, what's happening with the building, and that actually makes us some similar triangles. So let's take a look at how this all plays out. Okay, you have, actually let me do this way. Okay, so right here's a little picture. Okay, it goes with our word problem here. Okay, you notice that the building casts a shadow that is 8 feet long. We're not even considering the 40 feet wide building. We're looking at the height of the building. The building is casting an 8-foot shadow. And here's your friend. It says your friend is 5 feet 6 inches tall. But over here I have that your friend is 5.5 feet tall. Think this through for a minute. 5 feet 6 inches. 6 inches is half of a foot. That's where the 5.5 feet tall comes from. And this is my bad drawing of a person. And is casting a 3-foot shadow. So I need to figure out, we have similar triangles here. We have a right angle. We have the 3 feet and the 8 feet. Okay, these are similar triangles. They have the same thing happening. The sun is coming down at the same angle. So there is an angle up here and the angle down here are both the same angle. So these triangles are similar. That means that 3 has to go with 8 in the same way that 5.5 goes with H. So we have this right here. I want to try to expand this a little. Here we go. 3 goes with 8, just like 5.5 goes with H. So what we can do then is we can solve that so you get 15 feet. 15 feet is the height of the building. But we're thinking about painting the front of the building. The 8 feet is not part of the building at all. That's the shadow. The shadow was only useful to help us find the height of the building. Now that we have the height of the building, we can take into account the 40 feet. All right, this 40 feet is the front, along the front, and the height of the building is 15. 40 feet this way, 15 feet up. So the area of the building that you're trying to paint, and we're assuming no windows and all that stuff, we're making it simple, would be 15 times 40, which would give you 600 square feet. It said in your problem that that can of paint covers 400 square feet. but we're trying to cover 600 square feet. Since we're trying to cover 600 square feet and one can covers 400, if we divide that out, it tells us we would need 1.5 cans of paint. We can't buy a part can of paint, so we have to buy 2 of them. We're buying 2 cans of paint to cover the front of this building. So this right along the practical in this, another useful thing about this problem is figuring out the height of that building also might help you figure out what size ladder that you need to buy. Okay? Even those of you who might be having a call on your heart to go into missions, if you can use things like this, some proportions, you could possibly figure out and save yourself time and money if you for some reason have to paint some kind of a structure to help. A lot of times when we've been on missions trips, we've done painting projects. But if you can use little tricks like that to help you, it might help you someday. Maybe not, but it might. So these physical calculations can be very important, even when you might not necessarily think that they would be important. All right, so here we go. Here we have it. You're ready now for getting ready for your next week and for us to be in our home stretch here. It's a long home stretch, so you need to make sure you're ready for this last push through to the end of the year. I'm still praying that things can get together and we can have a little face-to-face time before the end of the school year. But we also want to be safe. We want to pray for wisdom for our people that are in charge that are making these decisions. But in the meantime, we can still love each other from a distance and pray for each other, which is what I've been doing, and I know that many of you have been doing that also for the teachers and the families, and it's so much appreciated whenever anybody reaches out. So with that being said, have a wonderful weekend, and God bless you.